In today's video, let's discuss the fundamentals of Monte Carlo simulation. The valuation of financial derivatives is a cornerstone of modern quantitative finance. Broadly, the methodologies for pricing these instruments can be categorized into three pillars: analytical closed-form solutions, numerical lattice or grid-based methods, and simulation-based techniques. Analytical models, exemplified by the celebrated Black-Scholes-Merton formula, offer elegance and computational speed. However, their applicability is confined to a narrow class of plain vanilla options under a stringent set of assumptions, such as constant volatility and interest rates. When these assumptions are relaxed or the derivative structures become more complex, analytical solutions are no longer available. This is where computational methods like Monte Carlo simulation demonstrate their unparalleled and powerful flexibility. The Monte Carlo method is a computational algorithm that relies on repeated random sampling to achieve the numerical results. It is an indispensable tool of choice for pricing derivatives with features that are difficult, if not impossible, to model using other techniques. These include instruments like path-dependent payoffs, example like Asian payoffs or barrier options, and high-dimensional problems involving multiple underlying assets like basket options, and models incorporating more realistic market dynamics like stochastic volatility or fluctuating interest rates. This adaptability makes Monte Carlo simulation a fundamental component of any financial engineer's toolkit. Now, let us look at the foundations of Monte Carlo simulation. At its most fundamental mathematical level, the Monte Carlo method is a numerical technique for evaluating complex integrals. This principle is directly applicable to finance through the concept of expected value. The expected value of a function of a random variable is, by its mathematical definition, an integral of that function over the variable's probability distribution. In the context of derivatives pricing, the risk-neutral valuation framework posits that an option's price is the discounted expected value of its future payoff. The primary objective of a Monte Carlo simulation in this context is therefore to approximate the expectation, and by extension, the underlying integral, by generating and averaging the outcomes of large number of random trades. Now, let the price of a European call option, for instance, given by the risk-neutral valuation formula be C is equals to e to the power of minus RT into E. The expectation term E is mathematically an integral from k to infinity of st minus k fst dst, where fst is the risk-neutral probability density function of the terminal stock price. For a simple European option under the assumptions of the Black-Scholes model, this integral can be solved analytically. However, for exotic options with more complex payoff structures, the integral often has no closed-form solution. The Monte Carlo method circumvents the need for analytical integration. It operates on the principle that by generating a large number of random samples of the terminal price ST and calculating the average of the corresponding payoffs, this average will converge to the true value of the integral. This reframes the method from a financial black box into a transparent and powerful application of fundamental statistical principles for numerical integration. The theoretical validity of the Monte Carlo method is anchored in the law of large numbers. This fundamental theorem of probability, as the number of independent, identically distributed random trials increases, the average of the outcomes of these trials will converge to the true expected value of the distribution. In the context of option pricing, each simulated price path for the underlying asset and its resulting payoff represents a single trade. By generating thousands or even millions of these paths, the simulation ensures that the calculated average payoff becomes a statistically reliable and accurate estimate of the true expected payoff. The more trials are run, the closer the approximation gets to the theoretical value, reducing the estimation error. Now, to build intuition, let us consider a task of determining the average payoff of a complex multi-sided unfairly weighted die. One could attempt to solve this problem analytically by meticulously calculating the probability of each phase landing up and then computing the probability of the weighted sum of all possible outcomes. This can be a complex task. The Monte Carlo method offers a conceptually simpler and computationally intensive alternative. Instead of performing the complex calculation, one could simply roll the die a million times, record the outcome of each roll, and then calculate the average of all recorded outcomes. This brute force simulation approach is the essence of the Monte Carlo method in finance. It replaces a potentially intractable analytical calculation with a large scale of numerical experiments. Now let's look at the general process of Monte Carlo. The application of Monte Carlo method, whether in finance, engineering, or physics, follows a consistent four-step process. First is the establishment of the mathematical model. We define the equation that mathematically links the input variables to the output variables. In option pricing, this involves two key components: the model for the underlying asset's price evolution, like the geometric Brownian motion, and the options payoff function, which is max of st minus k, 0 for a call option. The next step in the process is to determine the input distributions. We specify the probability distributions for all uncertain input variables. For a simple European option, the sole source of randomness is a shock term in the asset price model, which is typically driven by a random variable drawn from a standard normal distribution. The next step in the process is to generate random samples and simulate. We repeatedly draw random variables from the specified input distribution. For each set of random inputs, we run the mathematical model to calculate a possible outcome. This step involves generating a large number of potential future asset prices. The next step is that we aggregate the results. We collect all individual outcomes for these simulation runs and aggregate them to produce the final result. For option pricing, this involves averaging all the calculated payoffs and then discounting the average to the present value. The resulting distribution of outcomes also provides valuable information about the risk and uncertainty of the forecast. A critical concept in applying Monte Carlo simulation to derivative pricing is the distinction between the real-world probability measure and the risk-neutral probability measure. A common conceptual error is to simulate future stock prices using the stock's historical or expected rate of return, often denoted by the Greek letter mu. Such a simulation would produce a forecast of the stock's future price distribution based on its expected growth. However, the arbitrage-free price of a derivative does not depend on the underlying asset's real-world expected return. Two investors with different expectations for a stock's future performance must still agree on the price of the option on its stock today to prevent a risk-free profit opportunity. This conundrum is resolved by a cornerstone of financial theory, the fundamental theorem of no arbitrage pricing. In an accessible interpretation, this theorem states that in a market with no arbitrage opportunities, a unique risk-neutral probability measure must exist. Under this theoretical measure, the price of any derivative is its expected future payoff discounted at the risk-free rate of interest. This provides a universal and objective pricing framework. This theoretical leap from the real world to risk-neutral world has a simple but profound practical consequence for the construction of a Monte Carlo model. The mathematical formula used to estimate the stock price paths, the parameter of the expected drift, is replaced with the risk-free rate R. This single crucial substitution transforms the simulation from a forecasting tool which attempts to predict the future prices into a pricing engine that calculates the current arbitrage-free value of a derivative. This risk-neutral pricing approach is the bedrock of all modern derivatives valuation. Now let's look into the modeling of an underlying asset. To simulate the future prices of an underlying asset, a stochastic model describing its random walk is required. The financial industry's standard model for this purpose, particularly for pricing simple derivatives, is geometric Brownian motion. GBM is favored for several key properties that align well with the observed characteristics of the stock prices. The first property is that GBM implies that the stock prices follow a log normal distribution. This is a highly desirable feature because log normally distributed variables can only take positive values. The next property is that the basic GBM model assumes that the drift and volatility of the assets are constant throughout the option's life. While this is a simplification, real-world volatility is known to change over time. It makes the model mathematically tractable and serves as a robust baseline. The next property is that GBM is a Markov process, meaning that the future evolution of the stock price depends only on its current price, not on the sequence of prices that preceded it. This is consistent with the weak form of the efficient market hypothesis, which posits that all past price information is already reflected in the current price. Now, the general stochastic differential equation to model the dynamics of asset prices following a GBM is given as dSt is equals to mu into st into dt plus sigma into st into dwt, where u is the expected return and sigma is the volatility, where u st dt is a deterministic drift term, which states that over an infinitesimal time dt, the stock price is expected to grow at a continuous rate mu. And sigma st dwt is a stochastic or random diffusion component. It introduces uncertainty into the price part, with sigma representing the asset's volatility, and dwt is the increment of the Wiener process. Now, the analytical solution for this simulation or for this ST is the price of a stock at time t, st, is given as S0 into exponential function of mu minus 1 by 2 sigma square into t plus sigma into wt. This is the single most important equation for a pricer. Now, for the purpose of risk-neutral pricing, which we discussed earlier, we replace the real-world drift mu with the risk-free rate r. The Wiener process term wt is replaced by a discrete time equivalent z into root t. This gives the final simulation formula as st is equals to S0 into exponential function of r minus 1 by 2 sigma square into t plus sigma into z into root t. A noteworthy and often non-intuitive component of this formula is the r minus 1 by 2 sigma square term. Another assumption might be that the stock price in a risk-neutral world would simply grow at a rate r. The presence of the minus 1 by 2 sigma square term is a critical adjustment required by stochastic calculus. This term is called the convexity correction that arises from the properties of log normal distributions. It ensures that the expected value of the future stock price E correctly compounds at a risk-free rate. Volatility itself introduces an upward bias to the median of the price distribution, And this term corrects for that bias to ensure that the mean behaves as required by the no arbitrage principle. Now let's look at the core algorithm of Monte Carlo simulation. In this algorithm, we use multiple like S naught, which represents the initial price of the underlying asset, K, which represents the strike price of the option, T, which represents the time to maturity in years, R representing the annual risk-free rate, sigma representing the annual volatility of the underlying stock, n representing the number of Monte Carlo simulation paths, st, which is the simulated terminal price of the underlying asset, and z representing the random variable from the standard normal distribution n0, 1. Now the first step to this algorithm is initialization. We define the 5 core parameters as not k, t, r, sigma, and the primary simulation parameter, the number of paths to simulate. The next step is generation of random paths. We then generate an array of n independent random numbers with zi drawn from a standard normal distribution n0, 1. For each random zi, calculate a corresponding simulated terminal stock price st using the risk-neutral geometric Brownian motion formula. Now the formula for this is sti is equals to s naught into exponential function of r minus 1 by 2 sigma square t plus sigma into zi into root t. Now for each simulated terminal price STI, we calculate the option's intrinsic value or the payoff at the moment of expiration. The payoff of the function depends on the option type. For a European call option, payoff is equals to max into STI minus K, 0. For a European put option, payoff is equals to max into K minus STI. In the next step, we calculate the arithmetic average of all individual payoffs generated in step 3. This average represents the estimated expected payoff of the option at maturity. Average payoff is equals to 1 by n into sigma of payoff from I is equals to 1 to n. After calculating the average payoff, we discount it back to the present price, resulting the option price. So option price is equals to average payoff into exponential function of minus RT. This gives us the final result. Now let's look at the implementation of the algorithm in Python. This section translates the abstract algorithm into efficient practical Python code. For pedagogical clarity, the first implementation directly mirrors the step-by-step algorithm using standard Python for loop. This approach makes the connection between the algorithm and the code explicit and is easy for beginners to follow. So this function is pretty simple. We take in the parameters s0, k, t, r, sigma, the number of simulations, and the option type, and we define a payoffs list. After defining the list of payoffs, we iterate a loop for n simulations. Inside the loop, we first generate a random path. We initialize the random normal variable z and we calculate st using the formulas we discussed earlier. And we calculate the payoff based on the options type. Option type is called payoff is equals to max of st minus k, 0. The option type is put max of k minus st, 0. And we append these payoffs to the payoffs list. After that, we average and discount the payoff and return the option price. While the looped approach is intuitive, it is computationally inefficient in Python. A professional implementation leverages vectorization, where operations are performed on the entire arrays at once rather than element by element. This approach is significantly faster because the underlying loops are executed in highly optimized pre-compiled C code rather than in Python's slow interpreter. The shift from interpreted Python loops to compiled C loops is the source of dramatic speedup. Furthermore, modern CPUs are designed for single instruction, multiple data operations. Vectorization allows NumPy to leverage these hardware features, performing the same operation on multiple data points simultaneously. This transition represents a fundamental shift in the programming paradigm, encouraging the financial engineer to think in arrays to solve the computationally intensive problem efficiently. Now let's look at the vectorized Monte Carlo European price. Here, we generate all random paths at once. Using this line, we generate an array of random variables and store it in Z. Now, using this array of random variables, we generate another array of terminal prices and store it in ST. Now, if the option type is called, we generate the payoffs, which is np.maximum of ST minus K, which is np.maximum of ST minus K, 0. It is not called payoffs is equals to np.maximum of K minus ST, 0. Now, after this, we discount the mean of this payoffs array to the risk-free rate and time. After calculating the payoff array, we discount its mean to its present value and return the option price. Now let us simulate this using parameters s0 is equals to 100, k is equals to 105, t is equals to 1 year, r is equals to 5%, and sigma is equals to 20%. And n simulation is equal to 1 million paths. We send these parameters to the two Monte Carlo simulation functions we defined earlier, which is the one which uses loop and the other one which uses vectorization. And we calculate the time taken for each method. And we print the results and the resulted option price also. If you can see, the looped implementation took around 3.2177 seconds, whereas the vectorized implementation only took 0.0361 seconds, which is very, very, very computationally fast. And the looped implementation's option price is 8.0186, and the vectorized implementation's option price is 8.0460, which is relatively very small difference, with both of them positing a relatively small difference. So the vectorized implementation is typically 50 to 100 times faster, a performance gain that is critical for practical implementation and risk management in trading, where millions of pricing calculations may be required. This video has detailed the journey of constructing a Monte Carlo pricer for a European option, starting from the first principles. The process integrated concepts of several domains: the statistical foundation of the law of large numbers, the core economic principles of risk neutral valuation, the mathematical model of the geometric Brownian motion for asset prices, and its efficient vectorized implementation in Python. By mastering the construction of this fundamental model, the financial engineer unlocks the capability to accurately value a vast universe of exotic and complex financial instruments for which no other reliable pricing model is feasible. This makes the Monte Carlo simulation a truly indispensable skill in modern quantitative finance.